Hi Year 11, this is our second lesson for the topic of functions. In this lesson we're going to look at the graph of a function. Now in our last lesson we looked at types of relations, independent and dependent variables, function notation, and piecewise functions. Now there's quite a lot to get through. We're going to start by looking at the features of graphs, including x and y intercepts, turning points, increasing and decreasing, and asymptotes. And then we'll finish off with domain and range and odd and even functions. Now when we graph a function, we actually graph y equals f of x. So remember, f of x is our function notation, but we don't put that on the y-axis. This always remains y. So this is the graph of y equals f of x. And in this case, f of x is x minus 2 in brackets x plus 2 all squared. Now often we are asked to show the relevant features of the graph, and this can include x and y intercepts, turning points, asymptotes, and places where the graph is increasing or decreasing. So let's have a look at this example again. We want to identify the y-intercept, the x-intercepts, the turning points, and where the graph is increasing. So the y-intercept occurs when the curve cuts the y-axis. And it cuts here at y equals -4. We could write y equals -4, but it's better to write it as a point. And the point is 0, -4. The x-intercepts occur where the curve either touches or cuts the x-axis. And that happens here at -2, 0, and here at 1, 0. The turning points, that's where the graph turns around. So that's here and here. So that's -2, 0, and 0, -4. And finally, where the graph is increasing. So as we're going from left to right, where is the curve going upwards? And that's all of this part here. So x is less than -2, and all of this part here. So x is greater than 0. We can also find the x and y intercepts algebraically. To find the y-intercept, we substitute x equals 0. To find the x-intercepts, we substitute y equals 0. It's all very well just to memorize that. It's really important that you understand why that is. So looking at a simple graph, here's the y-intercept here. That happens where x is equal to 0. Here's the x-intercept. That happens when y is equal to 0. So here's our previous example, our previous function. F of x equals x minus 2 in brackets x plus 2 all squared. Let's find the x and y intercepts. I'm always going to start with the y-intercept because it's easiest. We want to substitute in x equals 0. So 0 in here and 0 here. That's going to give us -2 multiplied by 2 squared, which is -8. We're going to write it as a point, which is 0, -8. To find the x-intercepts, we substitute y equals 0. Now remember, this is y. So the 0 goes in here. So 0 equals x minus 2 multiplied by x plus 2 all squared. So that's a null factor law. Either this bracket is equal to 0 or this bracket is equal to 0. So what makes 0 here? 2, and here -2. So the points are 2, 0 and -2, 0. Now, until we learn calculus, we can only use the graph of a function to find any turning points. There is one exception, and that's parabolas, where we can use the formula for the axis of symmetry, and that's x is equal to -b on 2a. Now remember, with a parabola, they're symmetrical about the axis of symmetry, which is here, and so that's going to give us the x coordinate. And then we just substitute into the actual function itself to get the y coordinate. Let's look at a couple of examples. Find the coordinates of the turning point of y equals x squared take away 4x plus 7. And we've got the formula up here. So we're going to substitute in b is equal to -4 and a is equal to 1. So that's going to give us x is equal to -4, which is +4, all over 2 times 1, which is 2. Now substitute the 2 back into here, and we can write y of 2, just like function notation. 2 squared is 4, take away 8 plus 7, which gives us 3. So our turning point is 2, 3. Now, if it's already factorized like this, I'm going to show you another trick. We know the x-intercepts here. They are 1 and -3. And the turning point is going to be halfway between them. So the turning point occurs halfway between the x-intercepts. We also call the x-intercepts zeros. So the x-intercepts are 1 and -3. And so just doing the average of that, 1 take away 3 is -2, divided by 2 is -1. So rather than expanding it all out and then using the formula, you can just find the point that's halfway between. That will give you the x coordinate. You now need to substitute it back into here to get the y coordinate. We've got 1 take away -1, that's 2. And then -1 plus 3, that's also 2. So that's equal to 4. So the turning point is -1, 4. Now at this stage, we can only see increasing or decreasing regions from the graph of the function. And we did a question like that just before. But shortly, we're going to be using calculus to determine this. Let's move on to asymptotes. An asymptote is a straight line that the function approaches but never meets. And it's shown on a graph as a dotted line. Now, there are asymptotes that aren't straight lines, but we're not going to cover them in years 11 and 12. Now, this particular graph has two asymptotes. It has a vertical asymptote at x is equal to -1 and a horizontal asymptote at y is equal to 2. Now, to find vertical asymptotes algebraically, all we need to do is look for any x values that will give a denominator of 0. In this case, x plus 3 can't equal 0 because we can't divide by 0. So x can't equal -3. And that's actually our asymptote. Our asymptote is x equals -3. Now this question is a bit of a trick. This one doesn't have any asymptotes because it doesn't have a denominator. How about this one? This one has two asymptotes. There's a problem when x is equal to 1, and there's a problem when x is equal to -2. So the asymptotes are x is equal to 1 and x is equal to -2. But horizontal asymptotes are more difficult to find algebraically because we're looking for y values that cannot exist. And y is not on the denominator. It's easy with x. One thing we can do is actually switch them around. So I can take this x plus 3 and switch it with this y. Now in reality what I'm doing is multiplying both sides by x plus 3 and then dividing both sides by y. Rather than doing all that work, let's just switch them. X plus 3 is equal to 2 over y. Now I can easily see that the asymptote will be at y is equal to 0. What happens when we get a question like this? I can't easily move this x minus 5. I'm going to do one extra step. I'm going to take this 3 over first. Y take away 3 is equal to -1 on x take away 5. Now I can switch this and this. Gives me x minus 5 equals -1 on y minus 3. Where's the asymptote? Hopefully you're telling me at y is equal to 3. Okay, let's move on to domain and range. The domain of a function is the set of possible values for x. So let's have a look at a graph. This is a semicircle, and it has a domain of -3 is less than or equal to x is less than or equal to 3, or we can write it in interval notation like this. But basically we're looking for which x values does this graph exist for, and it's all of these. For all of these values I can find a y value that corresponds, but I can't find one here, I can't find one here. The range of a function is the set of possible values for y. Same graph. This time we're looking for the possible y values, and it's all of these. For all of these y values, there's a corresponding x value. In fact, there's 2. So this has a range from 0 up to 3. We can also work out the domain and range of piecewise functions, like this one. Remember this question from last lesson? It's got a variety of functions over different domains. But if we're looking for the overall domain, We're just looking for any x values that don't have a corresponding y value, and there are none. So the domain is all real x. Now for y, for the range, we're looking for any y values that don't have a corresponding x value, and that's anything below the x-axis. So our range is y is greater than or equal to 0. Now many functions have a natural domain of all real x, or in soft brackets we can write negative infinity to positive infinity, like these three. Straight line goes on and on forever. There's no x value that doesn't have a corresponding y value. Parabolas as well. There's no x that I can think of that doesn't have a corresponding y value. And cubics. We can restrict the domain of a function. So here we've got a cubic, y equals x cubed plus 1, and I've restricted the domain to be between -1 and +1. You can see how it's stopped the graph. What is the range in this case? We're looking for the y values. Can you see that it goes from 0 up to 2? Now what happens with domain and range if we've got asymptotes, like this question? Here we've got an asymptote at x is equal to -3 and another one at y equals 0. You could write it using inequalities. X is less than -3 or x is greater than -3. But it's easier just to state what x isn't equal to. And this implies that every other value is okay. So for our range, we would write y is not equal to 0. And finally, we need to look at functions with square roots. They're going to have a naturally restricted domain because we can't have a negative underneath the square root. So our domain is going to come from x minus 1 has to be greater than or equal to 0. So therefore the domain is x is greater than or equal to 1. And we can see that from the graph. Now with the range, you know how we normally have plus or minus the square root of something? Here we have no sign, which means it's the positive. So y is greater than or equal to 0. Let's try one more. State the domain of the following function, 1 divided by the square root of 1 minus x. So we have a denominator, which can't be equal to 0, and we have a square root. So 1 minus x must be positive. It must be greater than 0. Solving this, let's bring the x over the other side. 1 is greater than x, so the domain is x is less than 1. All right, let's move on. There are two types of functions that we name based on their symmetry. There is an even function, which has line symmetry about the y-axis, and it has this quality, f of negative x is equal to f of x. And there's an odd function, and it has rotational or point symmetry about the origin. You'll have to remember back to year 7 for that one. And it has this quality, f of negative x is equal to negative f of x. So let's have a look at these and see if we can figure out which one is odd, which one is even, and which one is neither. Let's start over here. This is the even function because we can fold it in half over the y-axis. It has line symmetry. This one here is the odd function. It has point symmetry about the origin. If I bring this part of the graph and rotate it 180 degrees, it's going to match this part here. So this is an odd function. And this one is neither. It looks like it might be even because we can fold it in half, but the axis of symmetry is not the y-axis. So this one is neither odd nor even. Now we can also prove that a function is odd, even, or neither by using algebraic methods. Here's an example. All we do is substitute in negative x for x. So I've got f of negative x is equal to negative x all squared, don't forget your brackets, plus 4. Negative x all squared is positive x squared. So x squared plus 4, x squared plus 4. This is equal to f of x. And that's that condition for it to be an even function. So the function is even. Now here's the graph. We can see how it has line symmetry. I just want to point something out to you. Suppose we choose any negative x value, like -2, and find the y-coordinate. That's 8. It is exactly the same as the y-coordinate for +2. And that's actually what this means. Here's another example. Is the function f of x equals x cubed plus x odd, even, or neither? Okay, same method. Let's substitute in negative x for x. I end up with negative x all cubed plus negative x. A negative cubed is a negative. So this is negative x cubed take away x. Does it match? No, so it's not an even function. My next job is to factorize this negative out. So I end up with negative bracket x cubed plus x. Now it matches. Can you see that? So this is negative f of x, and that is the quality of an odd function. Here's the graph. We can see that it has point symmetry about the origin, but let's have a look at a negative value, say negative 1. The y-coordinate is negative 2. Positive 1, the y-coordinate is positive 2. So same value, but different signs. That's what this means. Okay, did you notice a pattern there? F of x equals x squared plus 4 is even. F of x equals x cubed plus x is odd. Well, odd powers are going to be odd. X cubed plus x to the power of 1. Even powers, or powers of 0, this is 4x to the 0, will be even. But those rules don't work with a function that has a numerator and a denominator. See, at first glance here, we think odd function, even functions. This one will be neither, but it's not actually true. If we substitute in our negative x, we get 2 lots of negative x all over negative x all squared plus 1. And tidying that up, I get negative 2x all over x squared plus 1. And this is the negative of that. It's equal to negative f of x. So this function's actually odd. Okay, that's it. Our next lesson is on linear relationships.